Assalamu alaikum, bismillahirrahmanirrahim. Well, this is lecture number 28, the last lecture of your session. I just try my best to explain each and every point, but still, the HVAC subject, especially HVAC subject is very physical subject, and you have to, if you see the physical machinery, all the equipments, then it will very easy to visualize all the systems. Anyway, I try my best to explain with animations, with real pictures, with animated pictures, etc. Well, lecture number 27, and at the load estimation. Load estimation. So you can see at your homes that before selecting your home ACs 1 ton, 2 ton, there is a convention, a standard stable charts that represent only the area of the room. Like if your room area 12 by 8 feet, 1 ton AC suitable, and if it is a larger room, 2 ton, and so on. But to design the actual system in a commercial building for central air condition, we have to pinpoint each and every aspects that produce heating, whether it is a sensible heat or latent heat. We already discussed in the last lecture. Sensible heat is directly producing heat inside the rooms or space, and the latent heat is adding the moisture content in the air that is needed to remove in air conditioning process called dehumidification process. And by air conditioning, by cooling the air, all naturally air get dehumidified. And I could just give an example of cooling chilled water. If you have a chilled water bottle you place outside from the refrigerator, you see that water bubbles surrounding that chilled water bottle. So why? Because air on the air containing that low temperature around 12-11 degrees centigrade water, it get condense and comes into the real state of water. So in the same way, this is the latent heat. So how we estimate the cooling load? By calculating the overall heat produced by the systems. And I just showed some equations, some equation in the previous lecture. But the second method to calculate or estimate the heating load, that can be compensated with efficient amount of cooling load capacity of chillers. We can calculate it by the psychometric chart. In the psychometric chart, in the last live session, lots of students are still confused about the specific humidity and relative humidity. So for that, I just give a very short review of sensible heat and latent heat, and then we will move towards our last numerical and psychometric chart details. So let's say that we have a 1 meter cube of air, like this. We have 1 meter cube of air. In this 1 meter cube of air, let's suppose it has a moisture content of 10 gram, or it's 10 milligram, because in real we have a very less amount milligram. So when this the air gets cooled down in refrigeration coil, when the air passes from this, the air temperature also gets cooled down. So due to the cooling of air, the overall volume of air get shorter, for example shorter. So the in the previous temperature, let's suppose in previous in inlet we have a temperature like 30 degrees centigrade, and after passing from this cooling coil, the air temperature becomes 15 degrees centigrade. So if the temperature, we have a 15 degree drop in the air temperature, so air temperature volume also shrink down. So if we go into the microscopic level, each molecule of air constrained water molecules. So water molecules are present in the air. If the size of the air molecules shrink, the water molecule state in the gases becomes shorter. The space becomes shorter for the water molecules, and it get more shorter when it's reached to the dew point. And after reaching dew point, the water becomes on its real state, on its liquid state at because the boiling temperature of water is 100, so the room temperature is less than 100, so it comes into the liquid state. So in this way, at 30 degrees centigrade, the relative humidity of air, let's suppose, have 70%. It means that it can thus we have 10 gram of air, 10 milligram of water, means that still 30% of 10 milligram can be held by this air at 30 degrees centigrade. Let's suppose we have a 30 milligram of air present in 30 degrees centigrade, and relative humidity we have 70%. So 30% of 10 milligram is 3 gram. So it can hold further 3 gram, that is total 30 milligram. But after evaporating 30 milligram or gaining 30 milligram of water at 30 degrees centigrade, it cannot hold further water. So if the water is added to the system, or in the opposite manner, if the volume gets shrink down, like from 1 meter to 0.5 meter cube, the relative humidity increased by 100% for 15 degrees centigrade. Let's suppose for 15 degrees centigrade, the relative humidity of a water becomes 100%. So if the water relative humidity goes to the 100%, it means that it cannot hold further water. And if the temperature further below to 15 degrees centigrade, like 14, 13, the amount of water is removing from the air in the form of condensed shape. Like you have experienced that water in any chilled water soda bottle or water bottle that comes out from the freezer, etc. So similar happen in our air conditioning system. Like we have a slide of this. When the air passing from this point, it gets cooled down, and due to the cooling, like the coil temperature is around what, 7 degrees centigrade. So the moisture, it collects the moisture, and water is removed from the inside here. How it is represented in the psychometric chart? For psychometric chart, this is only one numerical I will cover in lecture, and remaining 2 to 3 numerical similar to this problem I will give as a homework for the practice for the paper. And this type of question will definitely come in the paper, because only one numerical is covering whole HVAC. Okay, so this is very important numerical. Further, I will request or suggest you people to watch this lecture in big screen, like for LED 32-inch LED, or minimum on the laptop, but not in the mobile screen, because we are going to solve it through psychometric chart and getting data out of psychometric chart. So you can, even in the final paper, you have to download this kind of a psychometric chart, where you can get the values. The previous psychometric chart was a very simpler one, and it doesn't have very large quantity of values. So in paper you don't need to do interpolation to spend more time on the numerical. So you have to use this kind of a psychometric chart, where you get values easily. Okay, anyway, let's solve this numerical. The atmospheric air at the 36 degree centigrade dry bulb temperature and 75% relative humidity enters the cooling at the rate of 200 meter cube per minute. This is the volume flow rate. Okay, and the coil dew point temperature is 14 degree. I think I have just explained dew point very well in the last slide, that water get condensed into the liquid form, moisture get condensed into the liquid state when it's cooled down, and when the relative humidity is become 100%, then after cooling the water's condensed into the moisture condensed into the liquid. Anyway, that temperature is 14 degrees centigrade, and the bypass factor of the coil is 0.1. That I will explain later. Determine the temperature of the air leaving the coil, capacity of cooling coil in tonnage of refrigeration, and kilowatt, and the amount of water vapor removed per minute. Okay, so these three quantity we will going to calculate. We are not calculating the sensible heat factor because it going into the further details which we are not covering in our course, and it is not in our course. We have to calculate the capacity of cooling coil, that is in our course content. Anyway, in this numerical you just come across one new parameter, that is BFF, bypass factor of a cooling coil. What is this? Basically, it is a part of a total air through the coil which fails to come into the contact with the surface of the cooling coil. Apparatus dew point ADP is the effective surface temperature of a cooling coil. Okay, and the formula is, let me just explain with you with the some soft diagram. Let's suppose this is the refrigerant pipe. Actually, before that I have to show the actual cooling coil. This is the actual cooling coil. The air is passing from this cooling coil. In the inlet we have might be refrigerant that cools this air, or might be chilled water. Both possibilities possible in air handling unit. You already said type of a chiller. So in any process, either we have a refrigerant or chilled water, it's cooling the air. So when we just see that it is a very on a closer note, you see that let's suppose this is the pipe where we have a let's suppose this is the pipe where we have a refrigerant is going through like this. It bends to another tube like this, and then so on. Air is passing through like in this way. So if we just see the closer look, there's a gap in between where the air is passing. Above we have a pipe which has a refrigerant, and below also again we have a pipe which have refrigerant, and it between these two pipes we have some vacant space where the air is passing and also exchanging heat from refrigerant to the air or chill water to the air. So you can see that in this gap it is not possible that all the air contact with the chilled water pipe and get cooled down. So there will be some difference. That's why parameter BPS, bypass factor, is used. From this formula, the bypass factor is equal to TD2 is a final temperature, let me just erase it. Yes, TD2 is a final temperature of a air, and TD1 is a inlet air. Just let's suppose air is passing in this direction. It enter here and pass out from the back side of this cooling coil. So let's suppose not suppose the TD1 is, this is TD1, temperature of inlet air, and this is TD2, and this is the bypass factor BPF, and ADP is a dew point. It is the temperature of skin of the pipe, okay, where the water is condensing. At the metal surface of the pipe, and when the moisture is condensed, it drop in the trays, and from the trays we just remove from the air handling unit, and you can see that the similar operation done in our indoor AC. Okay, So let's move out further in this numerical. As told before that in the psychometric chart numerical, you have to use this kind of a psychometric chart. So in the previous slides, we just get to know that how to reach the point where our current system is lying. So as per condition, we just need two information. One is dry bulb temperature, another one is relative humidity, or if the relative humidity is not available, if they given wet bulb temperature, then still we can come across to the our current position. So as per our current position, we have a 30 degree centigrade here. We just draw the vertical line from here, straight vertical line, yes, till the 70% of relative humidity. You see that this is our actual point where the system is in the current position before crossing the cooling coil. And after crossing the cooling coil, the temperature cools down like this. So this we have to draw a straight line like this, and in this in when the air is cooling, you can see that sorry, relative humidity is increasing. Why the humidity is increasing, I'll explain in previous slides. Because the volume of the air is getting shorter, so of course the holding capacity of air of a moisture getting lower. So when it reaches the 100% relative humidity, it cannot hold further moisture, and then still we are shrinking the size of the air. So what's happened, water moisture present in the air condensed into the liquid state. That is a dew point. Okay, and the coil is cooling the air till 14 degree centigrade. This is 14 degree, yes, you see that the mark is lying over here. Okay, so the cooling coil cools down the air to the 14 degree centigrade dew point, ADP, that is ADP. But you can see that not all the molecules can come across the pipes of the cooling coil, so there will be some difference. Some of the air slip as it is and then combine with the 14 degree centigrade. So how can we the first step, we have to calculate the outlet temperature of a air. So let's solve this numerical. We apply the same formula, BPF is equal to TD2 minus ADP. ADP is 14 degree centigrade. Okay, oh no, at the slide end, sorry. Yes, here we have to solve the numerical. Why it is not erasing? Yes, so first of all we have to calculate from BPF. BPF is equal to what, TD2, that is the final temperature, minus ADP. ADP divided by TD1 minus again ADP. So BPF value is 0.1. This is 0.1. So we have to write 0.1 over here, and we have to find out TD2 minus 14 is the dew point, and TD1 is 30 degree centigrade minus 14. By solving this equation, you get the TD2 value is equal to 15.6 degree centigrade. Okay, this is 30. Okay, now and we have to make one more. Yes, so we get the final temperature, that is TD2 is 15.6 degrees centigrade. So 30 degrees centigrade of air enters in the cooling coil and leaving the cooling coil with the temperature of 15.6 degrees centigrade. And the surface temperature of the cooling coil is 14. So due to the slippage of some air, the overall temperature of the outlet here is 15.6. Okay, now we have to calculate the cooling capacity of a cooling coil, and for that purpose we have to see the yes we have to see a psychometric chart. Okay, now the first thing we have to calculate is enthalpy. This is enthalpy. Okay, the lines which have angle of 45 around. Okay, this is the values of enthalpy, and the unit of enthalpy is kilojoules per kg, that you already done in thermodynamics. So we can easily calculate the heat Q is equal to m H2 minus H1. Okay, and another thing which we need to calculate is mass flow rate, and for the mass flow rate we also have to calculate the specific volume, the volume divided by mass kg per unit kg. Okay, in from this graph you can also get the value of specific volume, that is a specific volume. Okay, so they just given in a data 200 meter cube per minute the volume flow rate, and from that we can easily calculate the mass flow rate. So this is the 0.85, this is 0.90, and if we just make the line parallel to this line like this, you have to solve it in the paper. Okay, and draw the parallel line to it, and then or you can also draw the multiple parallel lines, and just make appropriate value, like the values lies over here. So this is 0.85, the center is 0.87 and 75 and 0.90. Okay, so we can just take the value 0.88. This is 0.84, 0.85, 0.86, 0.87 and 0.88. We just need to take the value 0.87. Okay, so this is the specific volume 0.87. Now let's see the enthalpy. The enthalpy value, you can see that it is in the middle of 80 and 85. So you can just take the value of enthalpy is 82. Okay, from this point you can easily get the value of enthalpy is 82 of H1. You can call that at H1, and from 2 point you can easily see the value, it is closer to 43.5. Yes, 43.5. Okay, so H2 is 43.5. Now what values is remaining? The specific moisture content. Now in this chart the moisture content is in the unit of kg per kg. That's why the values are in the decimal format. Like in previous chart we have a value like 10, 20. So if you divide 10, 20 with 1000, you get the similar values. Okay, so W1, the specific humidity unit is W, symbol is W. So you can see that the value lie on 0.1 is between 0.20 to 0.21. So you can just take the value 0.205. Okay, and W2, for the W2 you can just take the value 0.010, and you can take this value. You have to take value 15.6, not 14. Okay, 15.6. That's why we just take value of enthalpy is 43. Okay, Don't take value of 14. Your answer will be wrong. Okay, you have to make a straight line and scan the page if the paper is online, and if it is a hard form, you have to submit the psychometric chart as well. We will provide psychometric chart from the department. Okay, now we just get both value that I think we just get all the values. Now write down these values. Okay, we just write this in here, and we just get the enthalpy. H1 is 82 kilojoules per kg, and H2 value is 43. Okay, now first, and the mass flow rate, a specific volume is how much? 80. You can just take the specific volume, 87 kg per minute. It could be 88. You are just we just take the appropriate value, so there will be the tolerance of some values. I just don't want the accurate answer of this, because you see that in the chart there will be some tolerance of the values. So it is 87 meter cube per kg, and this is kilojoules per kg. Now, so first of all, we have to calculate the mass flow rate. The mass flow rate is equal to the volume flow rate divided by the specific volume. So this is meter cube per minute, this is meter cube per kg. So this will cancel out and it becomes kg per minute. Okay, so you from this you can get the value of mass flow rate around yes, you get the value of volume flow rate is 200 divided by, it is 0.87, sorry, this is 0.87. You can see, cross check the values. You say that it is 0.85 and this is 0.90, so I just now from this you get the value 227 kg per minute. This is the mass flow rate of the air. Now come to second page. If we divide by 227 with 60, you get the 227 divided by 60, you get 3.7 kg per second. Okay, now calculate the cooling capacity of a coil in kilojoules per kg. We know the formula, m h1 minus h2. The mass flow rate is 3.7 and h1 is 82. H1 is 82 and h2 is 43. Then from this you get the value 145 kilojoules per second, and you know that joules per second is watt, so it is similar. We just get the similar value of Q. 145 kilojoules per second means kilowatt. Simple. You get the cooling capacity of a cooling coil, so it is 145. But in the cooling capacity, normally AC are termed as a tonnage, so we have to convert this kilowatt into tonnage. So I'm not going to just derivate the kilowatts into tonnage. I just directly take the formula. 1 ton is equal to 1 tonnage of AC, your home AC or any cooling capacity device, is equal to 3.5 kilowatt. Okay, so 1 ton is 3.5 kilowatt. Just inverse this formula. 1 kilowatt will be 1 divided by 3.5 ton, means 1 kilowatt is equal to 1 divided by 3.5 ton. So 145, multiply 145 on both sides, you get the value of 145 kilowatt. Conversion into 145 now divided by 3.5, you get the value of Q in cooling capacity is divide by 145 3.5, so it is 41 ton. 41.4 ton. You can write this like this. Okay, so means that if that much amount 200 meter cube per minute is full, air is flowing with 30 degrees centigrade, relative humidity 70 percent, so it is cooling 44 ton, 41 ton, 41.4 ton. Now the last thing is we need to calculate is how much the moisture is removed from 30 degrees centigrade 75% relative humidity to 15.6 degrees centigrade of air. So just it is very simple. Just it is delta W is V1 minus V2. Simple. The V1 value is 0.02. You can take the value 0.025 for the more accurate purpose, but the 0.1 value is, you can see from this graph, sorry, yes, it is 205, and at 15 degrees centigrade, 15.6 degrees centigrade, it is exactly 0.011, 0.0205 0.2011. So we just divide these two values, 0.0205 minus 0.011. This, the unit is kg of moisture divided by kg of air. So the unit again have, it is a ratio kg divided by kg. So we just get the value of W2 is 0.0205 minus, so it is 0.0095 kg of dry air, kg of, sorry, moisture divided by kg of dry air. So if we multiply by mass flow rate, that is 226 kg per minute, 226 kg per minute. So kg will cancel out the mass flow rate of air, and we just get the amount of moisture removing per minute. So if we multiply it by 2.226, we get the value of 2.08 kg per minute. Okay, we just find out three quantities that need to be calculated. It means that 2.08 kg per minute is in a single minute 2.08 kg water is removed. It is a lot of amount, but you can see that it is not 1 ton, it is 44 ton. Okay, so this is cooling capacity. and you can also calculate the heat load of your rooms. Simply, if you have a 4 kilowatt of bulb quantity like 5, just multiply by 5 into 4 kilowatt, it is a sensible load. The human body radiates in the room. It's You can find the value of human body uh, sensible load from the HRA book, and you can also calculate the sensible latent heat of a human person, and just multiply with the number of person, add them, the values come in the form of kilowatt. Then convert this kilowatt into tonnage, then you get to know the required capacity of chiller should be installed. So I'm just giving you some it's already 27 minutes, so the lecture's getting pretty lengthy, so I'm just giving numericals to you. Just solve it. It's very simple numericals, similar to this problem, and similar problem will come also in the paper. Till then, Khudafiz, this is last lecture. I hope you all the best for the paper and for the sessional marks, etc. Thank you.